Okay, so we are going to talk about how to find the area between two curves. Okay, now we've already found the area between a curve and the x-axis. And so now what it is just finding it between two curves. And the important part is being able to set it up so that one curve has to be above the other curve the whole time and or below the other curve the whole time. And I'm going to show you a lot of examples of that. But so we are going to, let's look at an example first of all to look at two curves that we're trying to find the area between. So if I want to find the area between y equals x and y equals x squared from x equals 2 to x equals 4. Okay? So I'm going to, first of all, it's important to have a pretty accurate graph of this. So you can either graph it on your calculator or just be precise in your drawings. So for instance, on this one, we're going to need, so you have to think about how high you're going to need to go from x equals 2 to x equals 4. This one, I only need to get up to 4 and over to 4. Obviously on our x-axis, we're only from 2 to 4, so we don't need a lot of wide direction. But up and down, when x equals 4, this is going to be 16. Okay, so here I really don't need much. I just need 1, 2, 3, 4. I'm going to put 5 on there just for, so this is 1, 2, 3, 4, 5. And then here I need to go up to 16. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm still not leaving myself in a room. 11, 12, 13, 14, 15. Ooh, barely. 16. Okay? So, because what I want to do is I want to be able to graph this pretty accurately. So at 1, I'm going to be at 1. So this is first, I'm just going to graph y equals x. At 2, I'll be at 2. So I'm drawing this based off of how I drew my coordinates here. So 3 is at 3. 4 is at 4. So this, you can see that my y equals x graph is just going along at a slope of 1. I'm sorry, that's not super straight, but I tried. Okay, so then I also have y equals x squared. So it's going to go through 0, 0. It's also going to go through 1, 1, but the difference is here it's going to curve down before it goes through 1, 1. At 2, it's going to go through 4. At 3, it's going to go through 9. And at 4, it's going to go through 16. Okay, so I actually have this graph going out, okay? So pretend like I kind of went through my points. Okay, now the important thing is that you know just what those points are. So I'm going from 2 to 4. And so this is that area that I'm trying to find between the two. Okay, so before we just found the integral of the one equation, and that was telling us from 0 to, from the equation down to your x-axis, what the area was. Okay, now if you think about it this way, it's not too hard if you think, okay, well, the area from this upper curve, from 2 to 4 down to the x-axis, we can calculate that. And we can also calculate the area from this down to there. So if you take the upper area minus this little bottom area, then that gives you the area between the two curves. And that's essentially what you're doing. That's all that we are doing. But it gets a little tricky sometimes with certain circumstances, and that's why we're going to graph some of these and look at what can happen. Okay, so you can find the area by just doing that, by taking the integral from 2 to 4. And what I want to do is I want to find the integral up to this is the y equals x squared. And this was just y equals x. If I find the integral of x squared, that upper equation, and I subtract from it the integral of x, then that'll give me the area between the two. So that was just setting it up. That was a pretty simple setup. So as long as this one stays above that one the entire time, then you can just subtract them from each other. So let's evaluate too, just so we have a little reminder on how we find these areas and what we actually do. So we're going to take it, we're going to actually integrate this problem now. So we get x cubed over 3 minus x squared over 2, and we're going to evaluate that from 2 to 4. Okay, so to evaluate it from 2 to 4, we're now going to plug in 4. So 4 cubed over 3 minus 4 squared over 2. And then we're going to subtract from that 2 cubed over 3 minus 2 squared over 2. Okay, when you plug in those values, I'm actually not going to go through that process, but I just wanted to show you that you plug in your upper limit and into the entire equation, subtract it from your lower limit plugged in. You can go through that on your own of finding those values, but it's just 38 over 3. Okay, so that is the area between those two curves. Okay, so don't worry, the process is more complicated, but the same idea, it's really remains there the same. That so let's do a generalized rule. So let's do a definition. Okay, so if a region is bounded from, so if the region is bounded by f of x above, so notice that this has to be on top the entire time, and g of x below, it has to be on the underneath this equation the entire time. So at all points in the interval from A to B, and sorry, it includes A and B, then the area between them is the integral from A to B of f of x minus g of x dx. Okay, so as long as in that interval from A to B that there's one that is always, like if you were drawing lines that are vertical like this, it would always touch the first equation and then go down and touch the second equation, then you have just a very simple and basic integral between those two that you subtract. Okay, not too bad, right? Okay, so what happens if the area between the two is a little bit different? So let's see. Oh, so I guess this one, all it's asking you to do is, sometimes it doesn't tell you where those limits of integration are. So for instance, if it says just find the area between y equals 1 minus x squared and y equals 1 minus x. Okay, so in this case, because it doesn't tell us our limits of integration, you just have to find those yourself, which isn't too bad either. If you're pretty good at graphing, you can graph them on your calculator once again if it's in the calculator section. But so we're going to find the area that is in between those two graphs. Okay. Okay, so I think I actually just made my graph too big. That's okay. Okay, so on here, let's just make a little XY table for each of these so we can see what's happening with each of them to graph them. So if I plug in, let's just do -1, 0, and 1. If x equals -1 and you square it, you get 1 minus 1, so this is 0. 1 minus 0 is 1, and 1 minus, once again, that same value, which 1 minus 1, which is, you're back at 0 again. So I just want to, so this is an upside down parabola, right? And it's shifted by 1. So if you kind of know your graphs, it really helps too. But so we're going to start by just kind of graphing it here. So we have x is -1, then y is 0. And if x is 0, y is 1. And if x is 1, then y is 0. So let's see how this really is this upside down parabola. Unless we can do, let's go a little bit further so we can see, make sure we're kind of going in the right direction. So if -2, then this would give you a +4. So 1 minus 4 is a -3. And the same thing, 1 minus 4 would give you a -3. So by the time it gets to x equals 2, it's all the way down here to -3. And x equals -2, it's all the way down here to -3 too. It just helps to see how steep you should be graphing based off of the graph that you started. Okay, so then this one, let's look here. If we're at -1, 0, 1, I'm going to start kind of small again. 1 minus a -1 is 2. 1 minus 0 is 1. 1 minus 1 is 0. So let's start graphing this. Now this is a linear graph. It's just going to be straight. So we have at -1, the graph is at 2. At 0, the graph is at 1. And at 1, x equals 1, the graph is at 0. Okay, so if you can see in there, there's only going to be this one little section that the graph is going to cross itself at. Okay, so that's the little region that we're going to be graphing. So the limits of integration are going to be where these two equations equal each other. Okay, so if you graph it accurately and they come together like that, then you do know, we already kind of can see that these limits of integration are from 0 to 1. If you don't know that, we want to know where do these two equations equal each other, then you can set them equal to each other. So you have 1 minus x squared equals 1 minus x. And because of this x squared, it'll tell us both places that they're equal to each other. So here, let's see, so I'm going to have, I'm going to add the x squared to both sides. So I have x squared minus x, and then I'm going to add, I'm going to subtract that 1 from this side. So it'd actually just be right here. We want to know this would be 0. Okay, so then here, this would be x, and so I'm pulling an x out, so I just have x minus 1. So x equals 0 and x minus 1 equals 0, and we find that x equals 0 and x equals 1. That's where they equal each other. And we can see that here too, that they equal each other at x equals 0 and x equals 1. Okay, so that just means that our limits of integration are from 0 to 1. Okay, so we're going to set up our integral. First of all, we need to make sure that one of the graphs is always above the other one. So let's label which ones these ones are. So this is y equals 1 minus x squared, and this graph here is y equals 1 minus x. That just helps me so that you know which equation goes where. So on this one, if I'm drawing vertical lines, you can see that 1 minus x squared is always on the upper side. So that works out just great. So we have our integral from 0 to 1 of 1 minus x squared, which is the top function, minus the one that's on the bottom, which is 1 minus x. Okay, so when we can go through and actually, let's simplify that. So we're going to go 0 to 1, and I'm going to distribute my negative in here. So I'm going to have a plus x. Pretty much the same thing we did over there, actually. So pretty much if I distribute that negative in, I get negative 1 plus x. So I have 1 minus 1, which is 0, and I have the x. So I just have a positive x and a negative x squared. So negative x squared plus x. So I just combine together those terms. Okay, so now when we find the integral from 0 to 1 of this, we get, first of all, we're going to raise that. So we have negative 1 here, so negative to the third power divided by 3 plus x squared divided by 2. And we're going to evaluate that from 0 to 1. Okay, so then we're going to go through and we're going to plug those values in. So if I have negative 1 cubed over 3 plus 1 squared over 2 minus negative 0 cubed over 3 plus 0 squared over 2, you can see that this is actually just equal to, so 1 cubed is just 1, so we get negative 1/3 plus 1 squared, which is just 1, divided by 2 is 1/2, minus 0. Okay, so really what we have here is we're going to create a common denominator of 6. So, So if the denominator is 6, then this would be 2/6 is the same thing as 1/3. And if this denominator is 6, then this would be 3/6, which is the same thing as 1/2. So we'd have negative 2 plus 3, which is just a positive 1/6. Okay, so that area between those two curves is just 1/6. Okay, so I think we're going to start, let me do one more example, and we're going to start this section off with just where they have, you can actually cut them, where there's always above, one always that is above. So let's do one more example of just something else that you have to take into account. So find the area of the area, find the area of the area. What happens when I'm talking? Find the area between y equals sine of x and y equals cosine of x. Okay, so we're going to take, and we're going to kind of sketch a graph of those. Oh, and I am going to say that I want it just from, because obviously those actually go over each other a lot of times. So we want to go from 0 to pi halves. Okay, so I'm going to create a picture here for you of the two graphs. Both of them only go up to 1, and so I really only need 1, but I'm going to make it big so you can kind of see it. And then each of them, pi halves is going to get them just not even through their cycle. So let's see what we're going to do. So a normal sine curve completes an entire thing through 2 pi. So pi would be like one like mountain of the sine curve, and so pi halves is like up to the high point. So this one at pi halves, and that's how you can kind of think of it, as the sine will be at 1. And I'm making it really long so that you can see it. But so this one goes up to 1, and this is the equation y equals sine of x. It starts at 0 and goes up to 1. The other one is going to actually come down. It's going to hit 0 at this point. The cosine curve hits 0 right at that point too. So this is the curve y equals cosine of x. Okay, so now when you actually look at this, and we want to know what the area between the two curves is, it's going to be this area between them here. It's going to be here and here. Okay, so if we have that, where we have each of those, there's just something that you have to, so this is the first time you're going to actually have to think, okay, where is it above and where is it below? So notice that in this section, cosine of x is on top and sine of x is on the bottom. So if you're drawing these vertical lines, see how that's always on top until you get to that point where they cross. And here, the cosine is on the bottom the whole time and sine is always on top. And so we have to separate this out into two integrals, okay? So we have to pretty much, yeah, you do have to treat it like two separate integrals. So we're going to look at it from where they cross right here, which is at pi fourths. And we're going to have one integral. So we're going to have to do from 0 to pi fourths. It's going to have to be when cosine is on top. So we'll have cosine of x minus sine of x. And then we want to add to that because now we also want to know the area between the two on this side. So we're going to also add to that the integral from pi fourths, because now we're going from pi fourths to pi halves. And this time, the sine curve is on top. So sine of x, and we're going to subtract from that the bottom curve, which is cosine of x dx. So it's actually still not that bad as long as one's always on top. You just may have to, if they cross over and a different equation is on top, then you do have to separate it out into two. So we just calculate each of these separately is fine, and then add them together. So on here, when we integrate this, we get, so then we have the cosine, the integral of cosine is just sine. So we have sine of x. The integral of negative sine is positive cosine. And we're evaluating this from 0 to pi fourths. Okay, so when we have, and this we get, so first of all, the sine of pi fourths is the square root of 2 over 2. Plus the cosine of pi fourths, which is also the square root of 2 over 2. Let's see, did I do that right? Let's see, cosine of pi fourths is square root of 2 over 2. The cosine and the sine, so we're adding those two together, minus the sine of 0, which is 0, plus the sine of cosine at 0. The cosine of 0 is 1. Okay, so now I have, so I'm going to have minus 1 here. And what is the square root of 2 plus the square root of 2? When we add these two together, we get 2 square roots of 2 over 2 minus 1, where this cancels, so we have square root of 2. Oops, I'm totally off of the paper, sorry. Okay, so let's go back. So I took, what I'm doing is I'm evaluating. So I plugged in square root of 4 of pi over 4, and I'm subtracting with evaluated at when I plug 0 in. So I got square root of 2 over 2 plus square root of 2 over 2 minus 0 plus 1. And then, so what is square root of 2 plus the square root of 2 is 2 square roots of 2. But then you have the 2's cancel. So you're left with a square root of 2 minus 1, because right here we have minus 0 plus 1. Okay, so this is the area of this integral here. And we're going to need to add that to the area of this integral. Okay, so what is the integral of sine of x is negative cosine of x. And then negative cosine of x, the integral is negative sine. And we're going to integrate that from pi fourths to pi halves. Okay, so now we need to evaluate at pi halves. So if you see negative cosine of x, so we're going to have negative, and the cosine at pi halves is 0, minus the sine at pi halves, which is 1. And then we have to now evaluate it also, or now you're subtracting with pi fourths in there. And we knew before that the pi fourths, from what we calculated over here, well, it's similar, but negative square root of 2 over 2 minus the square root of 2 over 2. So here we have negative 0, which is a 0, minus 1. So we're going to have a negative 1 minus negative square root of 2 minus that is going to be negative 2 square roots of 2 over 2. The 2's cancel, the negatives cancel, and you're left with negative 1 plus the square root of 2. Okay, which is the same thing. Which is the same thing as the square root of 2 minus 1, right? So, and it doesn't actually matter so much. Anyway, so we're going to have now this. So now we have square roots of 2 minus 1 plus another square roots of 2 minus 1. So we should have known, and even just looking at that, because of how sine and cosine are, I mean, they're so even. That is, so those areas are equal. They both equal the square root of 2 minus 1. So when we get those, now we're going to add these two together. Okay, so the total area is going to be now square root of 2 plus the square root of 2, which is 2 square roots of 2. And then -1 plus a -1, which is -2. Okay, so that is the total area of the 2.